Good morning. My name is Jungwoo Kim, and I am an independent researcher affiliated with Gaon High School. I would like to express my sincere gratitude to NTUA for organizing this conference. Today, on behalf of our research team, including Eunjune Lee from Seoul National University of Science and Technology and Hyunmin Park from Gaon High School, I am very honored to present our research. The title of my presentation is Mathematical Modeling and Numerical Evaluation of a Wheel-Spoke Electromagnetic Energy Harvester. Now, let me begin with the research background. Most current research uses the piezoelectric method for energy harvesting. However, since piezoelectric generation relies on the mechanical stress applied to the generator or its materials, it is limited in harvesting higher power levels. In addition, to use the piezoelectric method for vehicle energy harvesting, it is necessary to create high-speed conditions for sufficient force on the generator. We analyzed two piezoelectric energy harvesters for vehicles proposed in 2009 and 2022. Model A was proposed in 2009. It used the Thundertrade piezoelectric generator to harvest energy from the wheels of the vehicles. As a result, it produces 4 milliwatts at 800 RPM. Model B, which was proposed in 2022, used a piezoelectric material to generate energy from stress from tire and wheel deformation. This method generated sufficient power, which can charge a 12-volt battery at speeds of 60 km per hour. Model A generated only 4 milliwatts at 800 RPM, which is insufficient for charging practical batteries. Furthermore, both models have severe limitations when it comes to generating at low speeds. Therefore, our research is aimed at designing and evaluating an electromagnetic energy harvester optimized for low speed and deceleration. We utilized the Euler-Lagrange equation to derive the governing equations of the system. The term representing the external force is expressed as the partial derivative of the integrate voltage with respect to the current. In these formulations, the displacement of the magnet and the electrical charge serve as the generalized coordinates. We analyzed and evaluated the mathematical design of the energy harvester through numerical simulation using Python. Now, let's move on to the methodology. The figures shown on the screen illustrate the detailed structure of the energy harvester. The figure on the left is a simplified structure of the wheel and harvester displacement. Shown on the right, the harvester unit consisting of a magnet, spring, and coil is strategically placed inside the wheel spoke of the vehicle. For simulation, we assumed that the length of the spoke is equal to the radius of the wheel, which is the distance from the center of the core to the surface of the wheel. We set a rotated angle, theta, measured from the vertical center line. When the angular acceleration of the wheel is constant, theta can be expressed as a function of time, angular velocity, and angular acceleration. Then, the position of the magnet with respect to the ground is given using a polar coordinate system. To get a Lagrangian, we represented mechanical kinetic energy, mechanical potential energy, and electrical potential energy in terms of the magnet's position coordinates, large X and large Y. We derived two coupled governing equations from the Euler-Lagrange equation, which uses the displacement of the magnet x and the electrical charge q as generalized coordinates. We set up our equations in terms of the electrical current and translational acceleration. Since the force of the magnet flux density B is function of x, the derivative of the magnetic field with respect to time should be expressed via the chain rule as the product of the derivative with respect to x and the translational velocity. In addition, we added the terms of elastic acceleration, which occurs from the force of the spring, and damping acceleration to the equation about translational acceleration. We used Python for conducting the simulation to get an optimum condition of the energy harvester. Simulation is composed of two cases. The first one is a case where the damping ratio is varied while the spring constant is kept constant. We observed peak power, total energy, and average energy with respect to the damping ratio in this case. The second case is a case where the damping ratio is constant while the spring constant is variable. Here, we observed not only the same power and energy metrics as the first case, but also the dynamic responses, including the positions and the velocity response of the magnet, and the oscillation amplitude of it. Now, let's move on to the result. As the damping ratio zeta increased, the peak power, total energy, and average power increased. In the total energy and average power graph, values initially decrease at small damping ratios. We attribute this initial decrease to the magnet position response error. In the simulation code, we embodied the physical boundary constraints as a strong repulsive force using the mechanism of elastic force. When zeta has a very small value, the centrifugal force becomes bigger than the repulsive force of the wall, and the position of the magnet exceeds its realistic translational range. Let's see the second case. The damping ratio is constant while the spring constant varies. Before the K gets to 500 Newton per meter, the same problem occurs, leading to numerical instability. The centrifugal force is bigger than the repulsive force, as in the first case. Therefore, values in this range were excluded from our system analysis and evaluation. After that value, peak power keeps decreasing while total energy and average power keep increasing within the evaluated range up to 5,000 Newton per meter. To analyze the tendency more accurately, we expanded the observing range from 3,000 to 10,000 Newton per meter. In this range, the graph of peak power exhibits a highly nonlinear and irregular behavior. It decreases until K reaches 4,000, then reverses to an upward slope until K reaches 6,000. After the value of 6,000, it has a local minimum at a point where K has the value of 8,500 Newton per meter. Total energy and average energy graphs are shown as monotone, increasing graphs according to the increasing K values. In addition, the slope of both the total energy and average power graphs continually diminishes, indicating a centration effect. According to the tendency of the total energy and average power graph, we expected the upper bound of the total energy and the average power to be 13 joule and 1.3 watts respectively. We analyzed the magnet's position and velocity to search for the reason for the generated energy behavior. In the position response graph, we can observe that the physical boundary constraints are violated in the cases when K is below 500 Newton per meter. After K reaches 500 Newton per meter, the frequency of the magnet's translational motion keeps increasing. In the velocity response graph, the peak velocity at 2000 Newton per meter is higher than the peak velocity at 5000 Newton per meter. This result perfectly coincides with the results in the peak power graph, a range of 100 to 5000. We also evaluated the oscillation amplitude and the root mean square value of the derivative of the magnet flux density with respect to time. RMS value of dB/dt is maximum when K equals 2400 Newton per meter. Also, the graph of oscillation amplitude is shown as a monotone decreasing function of K. According to Faraday's law, this maximum RMS value at 2400 Newton per meter represents the strongest electromotive force, and it leads to high generated energy. This result does not match the energy and power graphs. Since the frequency is proportional to the square root of K, increasing the K value leads to an increase in the frequency of the magnet's elastic motion. Therefore, we concluded that even though the RMS dB/dt diminishes beyond 2400 Newton per meter, the influence of the oscillation increasing frequency functions on the total energy generation is far more dominant than the effect of the decreasing RMS value. Now, let us conclude our presentation. An increase in K reduces the maximum displacement amplitude while increasing the system frequency. Consistently higher K values lead to an increase in total generated energy because of the dominant relative effect strength of oscillation frequency over the amplitude. In reality, due to nonlinear and irregular damping, an optimal K that maximizes the total energy can exist, and it should be verified in future works. Under ideal linear damping conditions we used for simulation, it is predicted that the total energy will astronomically converge to about 13 joule as K increases. Lastly, there are the key references that formed the foundational basis of our literature review, system modeling, and simulation parameters. Most of these articles deal with the harvester using the piezoelectric method. This brings me to the end of my presentation. Thank you very much for your time and attention. If you have any questions regarding our research, please feel free to contact us via email using the addresses provided on this page. Thank you once again.